will leave the floor to Antonio Fernández Anta, and please, thank you very much.
Thank you. I hope you can hear me. I'll try to be close to the microphone, but I don't know if I'm going to be able to do it because I'm very nervous when I present. I was very gladly surprised that I think our talk is going to be a very nice follow-up of Professor El Abadi's keynote, because he pointed out some of the problems that we somehow tackle in this presentation. So when I started learning about blockchain technology like 2-3 years ago, and I started asking people, what is blockchain and how it is used, and what is that? I got a lot of technical answers. A lot of the explanations I was getting were more on the mechanisms that are used instead of what exactly is a blockchain and what is the service that it proposes or it provides, and what is the underlying assumptions on the system. So there was a lot of confusion. You have a coin and you have the blockchain, but what is a coin? What is the blockchain? Do you need the coin for the blockchain? Do you need the blockchain for the coin? I mean, there was all this mess up. So sometimes, we were trying to check the specification. You found this, yellow paper that was, very, very technical, but not that easy to read and understand, what is behind it. And very often, all you had was a piece of code. So we have been, Chryssis, Nicolas, Kishori, my co-authors, we've been trying to think about the blockchain problem, or what is blockchain and blockchain concepts in a more fundamental and formal way from a distributed computing point of view, which is the community we come from. And we were glad to find out that we were not alone in this. So we found out very gladly that Maurice Herlihy, in a keynote in Pozzi 2 years ago, pointed out that there is a need of formalization in the blockchain world, and probably a need of reusing all the experience from distributed computing. Part of it has been done, the use of PVFT, the use of Byzantine consensus in various forms. But still, for instance, one thing that he proposed was the possibility of having universal construction combining specification and consensus protocol to obtain linearizable objects. In this particular case, that would be a blockchain which is linearizable. I'm going to talk about what linearizability means right now. So last year, we presented this paper or this abstraction, which we call a distributed ledger object. For us, we don't care about how it is implemented. In this abstraction, we only look at what service and also is provided. So essentially, for us, what you would call, or most people would call, a blockchain is just a ledger, which is a sequence of records. We don't want to call them blocks. We don't want to call them transactions, because if you look at the semantic point of view, what you have in a blockchain is a sequence of transactions. If you look at the implementation point of view, what you have is a sequence of blocks. So we try to avoid the discussion of whether these are blocks or transactions, and we use the concept of record. And we say, okay, we have this concurrent object, which you access through two operations. An append operation, in which all you're doing is adding one more record to the sequence, and you have a get operation that gives you the whole object, so you can, process locally. Of course, this get could be, you could create an API, a much more complex API if you want it. Do like, give me the third record, give me the last record, give me the length of the chain, whatever. But this was like, from an abstract point of view, to us was like a good starting point. So essentially, you append. So here you have two clients that are accessing this DLO, this digital ledger, and the client, the one on the left, can append a new record. The new record appears. He gets an answer saying, okay, your record was appended correctly. Then the other client can go and he gets a whole copy of the record, of the chain, of the ledger. Okay, so this is essentially the abstraction that I'm going to be using later, for the whole for the whole presentation. Of course, from an implementation point of view, if you want to implement this in a centralized way, the implementation is really, really, really simple. If you create this ledger in one single server, all you have to do is just, the server, all it has to do is receive appends whenever the record is not already in the sequence, is appended to the sequence, and then you respond saying, okay, everything went fine. Note that I'm assuming that the same record cannot be appended more than once. I don't think that is a restriction. Records could have like a unique identifier to make sure that you don't put the same record several times. And this is a very useful property. But this is again is probably like a implementation detail. And then get just returns this sequence. We also presented another more complex version of this DLO, which is what we call a validated DLO. In the validated DLO, we also have a valid function that is checked, executed on the concatenation of the sequence plus the new record before appending. So you only append a record that passes the validation test. This may seem simple, but actually with this validation, you can implement any of the current blockchains that you have now. Because this validation could, in fact, implement the validation test that you use for Ethereum, for Bitcoin, or for whatever you want, essentially. You can have, inside this validation, you can have an interpreter of the Ethereum machine code and make sure that, you're implementing an Ethereum, a blockchain or a DLO with the semantics of the Ethereum blockchain. So this is not a restriction. I'm going to forget about validated DLOs for now. I'm going to go back to the simple DLO in which we don't go into the semantics of the records. We don't know whether records contain transactions, whether they implement coins, they implement real estate registry, or they implement anything else. Okay? Of course, we want to go from a centralized implementation that I just presented to a distributed implementation, because that's what we, otherwise it's not practical, especially if you want to have this redundancy, and fault tolerance. So we're going to have our distributed ledger object is going to be implemented by a collection of servers that interact with each other. I don't call them miners because I don't want to put your mindset into proof of work. There are servers that interact and provide a service, which is this abstract API of append and get. Okay? So what we proved in that paper is that this can be done in a crash failure environment in which the membership of the collection of servers, which is a classical result. We were just like reusing already known system. And well, it's also very easy, and we are writing a draft for that, in which you can do it also with Byzantine failures. Essentially in a permissioned, let's introduce some terminology of, or let's reuse some terminology of blockchain. In a permission environment in which the membership, all the servers that are implementing the DLO or the blockchain, it's very easy to implement this DLO with the following properties, which are not usually provided. First, we have this strong prefix property, which essentially says that, whichever view of the sequence of records that I see has to be consistent with whatever everybody else sees. That means if I see two records in a particular order, everybody who sees the same two records should see them in the same particular order. This is not satisfied right now by Ethereum. It's not satisfied right now by Bitcoin. In Bitcoin, you can get a copy of the chain. You see a block, and then 5 minutes later, the block is gone. Why? Because there was a fork, and that particular block, was not in the winning branch of the fork. Okay, so I'm imposing something strong. As I said, in a permissioned system. For instance, Hyperledger Fabric that was mentioned before, Hyperledger Fabric does guarantee this property. And we have something that we call atomic consistency, or is also in generic terms called linear stability, which in vague terms means that if we look at the sequence of append and get operations issued by all the clients, it has to look as if the implementation is centralized. Meaning, if I append a record and that append operation completes, and somebody else later issues a get operation, they should see my record. If I append a record and Sarah appends a second record, everybody should see my record before her record. That's kind of the restrictions that we see in linear stability. Okay, it should be consistent with the real global clock, with real life, let's say. Okay, so I'm going to assume that we already have DLOs that guarantee these two properties. As I said, we showed how to implement that in a crash, under crashes. I don't care about how this is achieved, so I'm not going to go into proof of work, proof of stake, consensus, nothing like that. I assume that that is already solved by somebody else. I don't care for now whether the servers are crash, they crash, or they may crash, or they're Byzantine. That is solved for me. And I'm going to be working or interested about how I do connect these different DLOs. Why am I interested in interconnecting DLOs or interconnecting blockchain? I mean, I think most of you agree with me now that there's not going to be a single blockchain. I'm not saying blockchain technology, I'm saying blockchain. There's not going to be a single blockchain that is going to be ubiquitous and the only blockchain used in the world. For many reasons. First, scalability. Second, well, competition is good. Third, it's very, I would be very, very surprised if we all agree. Consensus is hard, especially at the global scale, right? So agreeing of one particular blockchain being used by everybody will be impossible. So we have to face the fact that we're going to be dealing with many different blockchains and blockchain technologies. So in this case, that's why certain problems and certain solutions have been already faced. One of them is what I call here atomic swap, which is something that was brought up already in the previous talk, in which essentially we have two clients, A and B. Client A has a good in a blockchain A, and he wants to send that good to, or pass that good to client B in that blockchain. And client B has a good in a blockchain DLO B, and he wants to pass that good to client A. But they want to do it in an atomic fashion. Essentially, they want to exchange these goods. So either both goods transfer hands, or no good changes hands. Which, it's a natural operation. So the solution right now is based on using what is called hash locks and time locks. So, well, I'm not going to go into the logic, but essentially the first client creates a secret and creates a smart contract. He puts his good in escrow, meaning he puts in a place where it cannot be touched until the smart contract is completed. And essentially, this smart contract is going to be completed when some secret is revealed. The other client, by looking at this smart contract, is able to generate another smart contract that uses the same secret to complete. As client B, he puts the good B in escrow, so it cannot be touched by her or by the other client until the smart contract is finished. Out of the two, only A knows this secret. So now when A reveals the secret to get GB, B can use it to get GA. Okay? So there are two things. One, they use hashing to preserve the secrecy of this secret X that is there, plus they use time, meaning there is a time t before this smart contract expires, and there is a time 2t before this expires. If things don't happen at the right time, there is a problem. We may end up finding that A got GB, but B didn't get GA. But they assume, in any case, what is being assumed is a synchronous system. This technique is already being used, for instance, to deploy this system called Interledger, where they want to transfer cryptocurrencies between any two blockchains, and it's also being used in Lightning and the Lightning network in Bitcoin in order to do like micropayments without having to actually update the Bitcoin blockchain. Also, Herlihy, that was also mentioned in the previous talk, generalized this to any collection of transactions that form a strongly connected directed graph, and he described how to build these smart contracts in order to have certain nice properties in this context. So what we do is we're going to take one step back. We don't have hashing, we don't have smart contracts, we don't have a synchronous system, in principle. We have DLOs. DLOs, which are just sequence of records, and we don't have any idea what every record contains. We don't care about the semantics of the record. Then what would be the right formulation of the same problem in this context? Well, in this context, what I have is, again, two clients, A and B. Each client has a record, which in the previous example may be this, I give you, record A, maybe I give good A to B. Record B could be I give good B to A, but I don't care. And what I want is to solve what I call the atomic appends problem, which, the way we define it, has two properties. One is, after the algorithm P is run, either both records have been appended to the respective DLOs, the respective blockchains. So RA is in DLO A and RB is in DLO B, or known, which is equivalent to say, both goods transfer hands or known. And I want some liveness in this property. This will be the safety part, and I want some liveness. If they don't fail, and I haven't talked about what kind of failures I'm assuming, if neither A nor B fail, this should actually complete, and both records should be added or appended in the DLOs. So we are going to assume two models. First, we're going to assume that both A and B are rational, but they are risk averse in the sense that they will not do anything whose worst outcome is losing. So they will always be very cautious in which steps they take. And we're going to have two models. One is called the competitive utility model, which essentially is the one we saw before. A is going to transfer the property of a card to B, and B is going to pay some money back to A by appending these records in the respective DLOs. And, for X, where X could be A or B, if X happens to find out that only the other one appended, he wins. Like, if A finds that B appended already the money without she transferring the car, then he doesn't do anything because he's rational and selfish. Okay? And he keeps the car and the money. So that is the best that can happen to either of them. Of course, they are interested in the transactions, so the utility of both appending is also good, but not as good as the other one. Another option is, okay, nobody does anything, so we stay the way we are. And of course, the worst situation for any of them is they do append, so they transferred, meaning they lose the property. So looking at an example, this would be the outcomes. One outcome is this would be like the initial situation. This would be the final situation if they both append. And this would be the situations if only one of them appends. One of them keeps everything, while the other gets nothing. Okay? So the problem with this setup is that due to the highly risk aversion that we assume from the players, from the two clients, nobody does anything. So we can prove that there's nothing, because we're assuming a system in which we don't have hash logs, we don't have time logs, we don't have anything like that. So we don't have the tools to guarantee to one client that if they append the record, the other one is going to do it, at least in this context. This is just, as you can see, this is an instance. Atomic swap, the example I gave before, is just an instance of this problem. So we come up with another version of the problem, a problem in which both clients are interested in the appends happening. And this is when we call it, this is the example of coordinating armies, and this is what we call the collaborative utility. The setup, I wanted to have an image from Game of Thrones, and when I was going to prepare it, I realized that I don't know anything about Game of Thrones. So I was not able to, I didn't want to, embarrass myself with, putting the wrong armies in the wrong side. So, but essentially, this is the coordinated attack problem. You have two armies, they have to coordinate themselves to attack a city. If one of them attacks by itself, they will lose the battle. They have to coordinate their attack so they both win simultaneously. Another example is you have A and B trying to buy collectively a property. If one of them tries to buy the property by itself, it doesn't have enough money. If they do it together, they get the property and they enjoy the fact that they have both properties. But if one of them backs up, the other one didn't really lose much, but the guy who backed up loses faith. I mean, loses credibility. Okay, so utility is the largest utility is when they both attack simultaneously because they win the city. If no one appends, okay, we stay the way we are. If only the other one appends, meaning the other one attacks the city, of course, the guy who attacks loses big time, exterminated. But the other army probably will be court-martialed. So it's not a good thing either. So it's better not to do anything than let the other one attack in without you. Because the other army will be destroyed, but you will be court-martialed or lose respect, lose credibility. So in this case, what we have is what we call a collaborative utility model. And in this case, the good thing is that in a failure-free system, all I have to do is just go ahead and append. If I know that nobody fails, I append, and I know eventually the other one will append because the utility of both appending is higher than only me appending. However, what happens if we introduce failures here? So we're going to look only at crash failures. If you want, eventually we may end up looking at Byzantine failures. But actually, I think the combination of crash failures with a rational behavior is rich enough for a first step. So, as I said, well, in a failure-free system, all they have to do is just they both append, and everybody's happy. Now, if we have failures, then things start getting interesting. Let's assume for now that only client A can append record A and client B can append record B. And let's assume that there can be at most one failure. Then considering an execution in which nobody fails, there can be at most one failure, but there could be execution in which nobody fails. Then by the liveness property, if nobody fails, we need to end up in a situation in which everybody has appended the records. So in a failure-free execution, RA must end up appending, and RB must end up appending. However, if one of them can fail, it could happen that we have exactly the same sequence of events, the same execution, up to the time that RA appends, and when that happens, RB crashes. We put a restriction that only RB can append in this DLO. So we failed miserably to satisfy safety, because we end up in a situation in which one of them appended and the other is not going to append. And we are not solving the problem. And in fact, this is a proof that this problem cannot be solved if at least, essentially we don't allow others to append. So the first relaxation of the conditions that we have is we assume that everybody can append, and then we show that in that case, by exchanging the records initially, you can tolerate one failure, and everything works fine. I'm not going to go into a lot of details, but essentially, I wait for the record from the other client, and when I have both records, I can safely start the appending process. The problem is if I'm going to stop. The problem is that if I implement this in asynchrony, it could happen that I wait forever for the other to send me the record and never make progress. So also, if both clients can crash, this exchange doesn't solve the problem. And I'm stepping quickly over this proofs because I don't have time. Okay, so essentially, we have several cases in which we don't have a good solution. We have the case in which players are competitive. I'm giving you money and you're giving me a car. We don't have a solution for that. We have the case in which there are crash failures and both of them can crash. And we have the case in which there is one crash failure, the system is asynchronous, and we don't want anybody to wait forever. These three scenarios cannot be solved right now. So with all the tools that we've been using so far, so in order to solve these scenarios, we're introducing a weak form of smart contracts, which essentially is what we call a smart DLO. So we are adding another DLO, another blockchain, whose purpose is only to coordinate this exchange or this append of records. So essentially, in this SDLO, it probably is simpler to look at the example. Client B is appending a special record saying, okay, I'm B, I'm involved in a atomic append operation with A, and this is my record. Then eventually, hopefully, A will also append a symmetric record, and when the smart DLO finds this, he knows, oh, I have all the ingredients to trigger the appends in both our DLO A and DLO B. And it's SDLO who does the append only when all the requirements are there. So this can be implemented with a smart contract, a simple smart contract. Okay. It solves the problem in many different setups, in particular the three that I just presented, but even in more cases. However, we are assuming something that is not standard in blockchain now, which is blockchains interacting with other blockchains. There is something called oracles that allow blockchains to get information from the outside world, and in particular, they could get information from other blockchains. But as far as I know, we don't have any blockchain that is actually able to issue operations in other blockchains. So we are assuming that. Actually, an implementation detail. SDLO is implemented with multiple servers. So who is appending? Which of these three servers is appending? Because SDLO is not one entity. It's an abstract entity implemented with multiple servers talking to each other. So in fact, if we have a crash, if the SDLO, if these servers can fail by crashing, it's okay if we all of them try, because we assume that operations are, append operations are idempotent. So if there are multiple servers, appending, I mean, as long as one of them succeeds, the others will not take effect and they will be fine. But if they are Byzantine, we have a problem. We have to take care of that, and we haven't thought about that enough right now. Okay. There are other systems in which they are looking at interconnection of different blockchains. There's Cosmos. There is this TradeCoin at MIT Media Lab, in which they try to use gateways. But I mean, just a conclusion. I think the broad view is that isolated DLOs, isolated blockchains are okay, but they're not going to be the final solution. We need to allow interconnection and interoperability. And well, I think the problem we proposed is a very simple problem, a very natural problem, and solving it in as many scenarios as possible, in my view, is an interesting issue. Well, we have a bunch of future work.
Thank you very much. There are some questions. Yes.
Hello.
Hi.
I have two questions, actually. The first one is formal. You defined an object which is a DLO. How do you compare it to the formalization of Garay in the Bitcoin backbone protocol in terms of chain quality and common prefix? What are the differences between...
The one by Garay?
In the...
You're talking I'm not familiar with it. I have to look at it. Sorry.
Okay.
I think at least the ambition is the same at the beginning. What they do is
I know. I'm not familiar with the definition.
the functionality before they describe an implementation.
Okay, I'm sorry, but I don't know if you guys are.
Yeah, that one is specialized on Bitcoin, how Bitcoin works, and the mechanics of the Bitcoin.
No, but no. At the beginning, they specify an object, which they describe in terms of chain quality and common prefix, and I found it very similar, so I was asking. But, and then
the common prefix is not ours actually. The definition is just like a common natural property. It's not like something that we came up with. But we took it. The latest version I took it is from a paper from last year. But yeah.
Okay. And then the second question is the slide just before. You said that a small DLO cannot make an append on another blockchain. So
no, he has to be able to do it.
Okay.
In our implementation, yeah.
So in your formalization, it should be able to make an append. Okay. So what you were describing is what we don't want.
You don't want it? Why?
Two concurrent servers making two different append. This is not possible.
Oh, we don't want making. We don't mind if they append the same record.
Okay.
Because I'm assuming that the DLO makes sure that if the same record is appended more than once, only the first one stays.
Okay.
If they issue. If the SDLO appends different records, they should be records that have to be appended, and that is fine too.
Okay, so it's part of the specification. It's directly implied by the specification of DLO.
The specification of DLO, the way we use it here, implies that append operations are idempotent. So if the same record is appended more than once, then only one of these appends actually takes effect in the sequence. Yeah.
Okay, thank you very much.
Yeah.
So maybe just other questions you want to put?
I have a question about the first part. Not the first part, the middle thing about the collaborative utility model.
Mm-hmm.
So then you proved that even the simple thing with the simple constraint is not possible.
Mm-hmm. With crashes.
With crashes.
With one single crash. Yeah.
Yes. How important is it that you are working under the assumption that they collaborate in the sense of your inequalities? Is it not always the case, whatever you ask them to do, that it's not going to work?
No, because if the system doesn't, if there are no crashes.
No, but with crashes, of course.
Oh, of course, but in the competitive case,
It's
even
worse.
without crashes, it doesn't work.
I understand, but you don't have to assume anything. You don't have to assume that they collaborate to prove it's still impossible. It's not possible anyway.
Well, I
it's my question.
prove that competitive doesn't work. So I say, if I move, competitive without crashes doesn't work. Collaborative without crashes, it works. Collaborative with crashes,
Yeah, so this
doesn't
one,
work.
But yeah, so I'm saying with crashes, nothing works. You don't have, even if you're, somehow if you had a way to make them more than collaborative in the sense of your utility.
No, but I mean,
inequalities.
I'm able to tolerate one crash if I'm allowed to delegate. So I'm able to tolerate crashes.
I see.
It just depends on the
So you win
on the
one
assumptions.
crash.
Sorry?
You win one crash.
Yeah. So yeah, some of the results are negative, some of the results are positive. Yeah.
The last question.
I'd like to ask, how can such an SDLO create new information that neither Alice nor Bob had in order to submit it to the other two blockchains?
It's not creating information, it's just providing reliability. SDLO, I mean, it's essentially what a blockchain is. A blockchain is just providing stable storage.
So if it doesn't create any new information, then upon when Alice publishes her part of the information, then Bob reads Alice's part of the information from the SDLO, does not send anything to the SDLO, and then just Bob will create this, will take Alice's asset, but Alice will not take Bob's asset, because Bob never appended his part on the SDLO, and Bob was able to do what the SDLO would do with and just the part that he would like to be done. You see my point?
For a collaborative, sorry, I'm not getting it. So they use the SDLO as an intermediate storage, or they append their record in their DLO. Can you repeat that?
Can you show the slide with the SDLO again? This one, yes. So this assumes that A and B are collaborative, or they are.
No.
Okay.
No,
so
the SDLO takes care of not triggering the append operations in the DLO A and B unless all the requirements are there.
Okay, so now in this exact slide, B has sent their part.
Yeah.
So A reads from the SDLO, and then A doesn't send her part, but sends to the DLO B the part that the SDLO would send.
Yeah, it's not obvious, but there should be some mechanism to prevent
That's where I'm asking.
A from using that. Yeah, it could be some signatures. We need some crypto here.
Okay.
Sorry. Yeah, good point.
So that means that not only your SDLO can communicate, but it can also authenticate. And the authentication can be recognized by your other DLO. That's a much stronger assumption. It means that all those blockchains know each other and they authenticate each other's messages. I think it's a very strong point.
Yeah, actually, this is something that we have to. I mean, we describe it in an abstract way. We need to complete it with mechanisms.
A last little point. So I'm not sure about this because it's not my expertise, but in cryptography, people tell you all the time that fair swap, which is essentially another name for safety, is impossible in their model. So, and they must have known this for 20 years. So you might want to check what they mean by this and compare with the way in which you define it, which may be slightly different.
No, I mean, actually, atomic swap, as I described it at the beginning, this is a very classical problem in crypto. Here, what we have is a new element, which is provided by this blockchain, which is the reliable. I mean, the fact that you have a reliable entity is what changes the game. But we just think that this is an interesting interesting element to study. And actually, this is something that also was brought up in the previous talk. I think I have it here. So the idea is that we may want to think about a blockchain system the way we think of a database system, where you have transactions that involve many information coming from many different blockchains and modify many different blockchains, and you want these transactions to be atomic. And implement, it would be great to achieve ACID properties the way you achieve them in databases, in a system, a whole system of blockchains. And that's a kind of like our view of what this is going towards, at least in the permission world. Permissionless is way more difficult to deal with, and we don't know.
So just a comment on that. You say that actually assuming risk-adverse clients or whatever, agents, do you think that if they could believe that there is a cryptographic mechanism or kind of timing assumptions and these kind of things, they could actually make different decisions?
Yeah, I mean, I didn't go through all the results, but some of the results assume synchrony, some of them assume asynchrony. Yeah, I mean, if you change the model, there will be different solutions. I'm sure that there are a lot of different variants of the problem that can be explored.
Thank you very much. So let's thank the speaker.